We now go over another example, this one coming from physics. There's the motion under the influence of gravity. Some of you may have seen these kind of problems before because it actually doesn't really require calculus, just algebra. But of course, if you use calculus, it becomes much easier. So here we're under the assumption that the gravitational pull is constant, which is a good approximation, good enough approximation when you're close to the surface of the Earth. Because what makes a gravity change as you approach Earth is the radius. I mean the distance from distance from the object to the center of the Earth. But given that compared to the radius of the Earth, small variations above the surface are negligible. You can pretty much assume that there's a constant which you probably have called G in physics courses. And this is exactly what we're going to do. We're going to assume that there's a constant acceleration pointing downwards. And as such, we're going to write down not the equations of motion. We're assuming that we already have the description of the motion of a particle. And so S here will be the position at time t. So it will be the height. G is pointing downwards. So this is the gravitational force. And ground level should be S equals 0. And at time t, you find yourself at height S of t. And of course, since S is changing, then there's a velocity. There's a change in position as time passes. And so these are the two things that describe the motion. The position and the velocity. The velocity just comes from derivating S of t. So in addition, we have to specify, otherwise the problem is not well defined. You cannot really know where you're going to be in the future or where you've been unless you know where you started from. So this is the S0 will just be the position at the time t equals 0. And you also need the initial velocity. This is very important. Otherwise, for instance, if you start with velocity 0, you're just falling further down from the beginning. And if you're at ground level, then you just don't move. So if we want to make something interesting happen, we need to generate an initial motion that is going against the gravitational pull. So hopefully V0 will be pointing upwards. Okay, so that's actually the situation we're going to have in this problem. Again, minus g, which is the acceleration. So roughly, I mean, this is the approximation. So we usually give students, this is 9.8 meters per second square. Of course, we're using standard units. And so for this problem, which is going to be rather short, and it has to do with rate of change. So if you toss something in the air, when do you expect, what is a condition that will tell you that you reach a maximum height? Maximum height will be attained, will be reached when the velocity is 0. So you start moving up because of the gravitational pull. You will start slowing down until you reach the maximum point, and that means that the instantaneous velocity is 0, and then you start going down again. So as you go up, the velocity is positive. When you're going down, velocity is negative. So at this point, when we reach your maximum height, velocity is equal to 0. So the tangent line, if you were to graph height in terms of time, this point here would correspond to this. So it's a point where the tangent line is horizontal. So and with this information and these observations at hand, we go to the example. So we toss a ball in the air vertically from ground level it returns to Earth 4 seconds. 4 seconds later. So the question has 2 parts. The first one, find the initial velocity. And the second one, find the maximum height. Okay, so let's solve the problem. We know that since we start from ground level, S naught is equal to 0. Okay, so then this means that S of t is simply given by v naught times t minus 1/2 gt squared. We know that S of 4 is equal to 0, which then implies that, remember that at time 4 you go back to Earth, to where you started, the point you started from. So if we plug this 4 into actually everywhere there is a t, we get s at that point, at that time, which is 4 minus 1/2 g times 4 squared, because it's the time. And that should be equal to 0, because at that time you came back to Earth. This is the same as saying as 4v0 minus 16 over 2 g is equal to 0. Here, of course, you may divide by 4 and obtain that, and move this to the other side, and obtain that v0 is equal to 16 over 8 times g, which is just 2g. And g, as we know, we said, has a known value. This can be approximated as 9.8. This is approximately equal to 2 times 9.8 meters per second, which is equal to 19.6 meters per second. Now B, what do we say? So when do we reach the maximum height? Okay, so now we have forgot. We have now the value of v0, so the initial velocity. It's computed just like that. v0, so v0 is 19.6 meters per second, more or less. So we already know the condition we need to impose when we are asked to find the maximum height. So this takes place when the velocity is 0. Prime of t is equal to 0. And we know that s prime of t is just a v0, so the initial velocity, minus gt. That's a formula we had at the beginning, which is then 19.6, which is what we found, minus 9.8 times t. In reality, this should be approximately equal to that, but we want to get some numbers, so we are going to just say the claim that g is 9.8. It's really close to that anyway. So now, remember, we want to impose that this is equal to 0, so we're going to impose that this is equal to 0, and that will imply then that t have to be equal to 19.6, 9.8, which will be equal to 2. And so now s of 2, we were asked about the maximum height. We first found the time at which this maximum height was attained. And now to find the maximum height, we just need to plug in the value that we found for the time, and we'll obtain the height at time 2. So 2 will just be equal to 2 times 19.6 minus 4.9 times 4. In case you're asking here, this 4.9 comes from computing g over 2. So this is 9.8 divided by 2. and times 2 squared. This is 2 squared. This is what the formula tells us. And so this gives us 19.6 meters. So just one more time, just in case there's confusion here. So we're just plugging this into the formula for S, which we found to be equal to V naught times T, but T here is 2, minus 1/2 G times T squared, which is 2 squared, and V naught was already found here to be equal to 19.6 meters per second. And so we do that 19.6.2 minus, and what is 9.8 divided by 2? G is 9.8 approximately, and then we have to multiply this by T squared. 2 squared. And this is equal to 4.9. Right? And this is exactly what we have obtained here. Just in case you were wondering, what are those missing steps? Okay, so that will be it for this lecture, and we'll see each other on Thursday.